Welcome to Ruipeng, who's going to talk about developments on the Hypre package of algebraic multigrid and linear solver stack.
Thank you for the introduction, the invitation to this conference. Really glad to be here. Today I'm going to talk about our still in progress work on porting the multigrid solvers, in particular the AMG solvers in Hypre, to the GPU platforms. So this is a joint work with a bunch of colleagues in Lawrence Livermore, and we have Chaoyu Zhang from Arkansas State, our former summer intern, and Keisha and Steve from Unreal, working on various things in Hypre. So all these current algorithmic and software effort in Hypre actually are due to the hardware change. So at Lawrence Livermore, we have this new supercomputer Sierra, which is I think it's still the world #2 in the top 500 list. It has a very different architecture compared to previous supercomputer. Each node of Sierra actually is very powerful. It has 4 Volta GPUs and 2 Power 9 CPUs. It has, compared to Sequoia, it has much fewer nodes, but on each node is the peak performance is much higher. And remarkably, more than 95% of the flops is actually on the GPUs. So to take advantage of this big machine, we really want to port the majority of our computation to GPUs. Yeah. So I'm going to give a brief overview of the GPU support in Hypre so far. So the GPU support has been available in the several recent releases of Hypre. So we started with the structured multigrid solver because things are nicer and easier there, because the computation can be organized in a more structured way. And these are enabled by various approaches like CUDA or OpenMP 4.5, Raja and Cocos for the portability purpose. And the structured multigrid solvers like SMG and PFMG has been fully ported to GPUs. And since our last release, we finally have one path of algebraic multigrid setup and solve completely on GPU. So today I'm going to cover the major components of Boomer AMG on GPU. So here I list the major ingredients of AMG that has been ported to GPU. So in the setup phase, it includes computing the strength of connection matrix, computing the coarsening, currently just one coarsening parallel maximum independent set on GPU. And we chose the simplest possible interpolation, which is direct interpolation on GPU first. And we compute the coarse grade operator by computing the triple matrix product. In the solve phase, we have relaxation. So it's based on what kind of smoother you choose, and the matrix vector product, and the coarsest grid solve. So here in this figure, just show briefly like all the time of these components in the setup phase can be shortened if you run it on GPU. So first talk about the PMIS coarsening on GPU. This algorithm is very suited for GPU because it's massively parallel. It actually computes a maximum independent set by using this Lubis algorithm. It actually random set a number to each node and compare this random number with its neighbors and find the local maximum and pick that point in the independent set. So I want to just point out we actually don't compute the maximum independent set in the Lubis algorithm. We just do one step of Lubis algorithm and keep the outer iteration going until we mark all the points, either C or F. So here is the performance of PMIS on GPUs. This is on a cluster with P100 GPUs with Power 8 CPUs. For 3D Laplacian, on each GPU, we have problem size 8 million. You can see both the CPU and the GPU performance scale well. This is a weak scalability study, and we more or less have speed up of factor 5. This is comparing one GPU with 5 OpenMP threading CPU version. Interpolation. So we started with the simplest direct interpolation. So the formula is very simple in the sense that you only need to look for each F point, you only need to look at the corresponding row of that matrix. And the interpolation weights is given by minus Aij divided by Aii, and you scaled by another factor to make sure you can interpolate constant exactly. We also tried, there's also a low-hanging fruit we can implement. Basically, there's no complication of implementing another version which is based on some BAMG idea proposed by Park and Mentelfo in 2010. What it does is it solves a constraint minimization problem. So here the E is some target vector, and you want to find, the constraint is you want to interpolate this vector exactly, and you want to minimize the deviation from AIC over AII. And if for the special case when E is a constant vector, it turns out you can have a nice modification of the direct interpolation formula by adding a term in the numerator. And turns out based on our test, turns out the second variant is usually better than direct interpolation. Next, going to talk about the most difficult part, which is computing the RAP on GPU. So we compute RAP in pairs. We usually compute AP first and then compute R and AP. The algorithm is based on classical row accumulation SpGEMM algorithm. So if C equals to AB, then each row of C is a linear combination of multiple rows of B. So in the CPU code, even for multi-threaded CPU code, a common approach is using some dense accumulator, but this is not possible for GPU because you have too many parallel threads computing the rows of C simultaneously. So a lot of work has been done to choose sparse accumulators. So we adopt a hash-based sparse accumulator, which is also used in a lot of works in literature. For example, I think the Sandia guy is also using the hash-based accumulator in the Cocos kernel. In addition to the difficulty of accumulating sparse rows, another difficulty in computing RAP is to deal with the dynamic structure of the product. Because of that, before the actual numerical multiplication, we do a symbolic multiplication first to actually just count the number of non-zeros of each row. It's okay to not have the exact number of non-zeros per row, but at least you should have a reasonable upper bound. This is done by doing some symbolic multiplication to just determine the pattern of the product. Okay, here I want to show some code, which is the core of our SpGEMM. It's a hash-based algorithm. So this code snap shows the hash function. So we have a hash table organized in arrays, and we have a key and value, which is the pair we want to insert. So keep in mind, this hash table is shared by multiple threads. So you may have simultaneous hash insertions from different threads into the same, potentially into the same position of hash table. So in the outer for loop, this for I loop is actually the probing, because you cannot guarantee each time you can successfully insert your value into the table. So each time you use your key and compute the hash function, using the hash function to compute the position j of it, and try to insert your key and value pair into that position. If it is -1, means that that position is empty, or that position happens to contain the same key of the one you want to insert, you can just update. Otherwise, you have to, that means there has been a hash conflict, hash collision there, so you have to keep probing. So we have done some work on choosing different hash functions and choosing different probing schemes, like linear or quadratic. Okay, after we have this CSR matrix multiplication on one GPU, so we can put them together to develop this distributed par CSR matrix multiplication. So in Hypre, the matrix is distributed in the way that each process owns a slice of rows, and the rows are partitioned into the diagonal part and off-diagonal part. So it actually, multiplying two par CSR matrix can be decomposed into a bunch of local CSR kernels, like matrix multiplications, additions, merging, splitting, etc. And also communications are involved to exchange the rows from other processes. So this is some experimental result comparing with the state-of-art GPU SpGEMM from Sparse, and also the implementation in Hypre, the CPU implementation in Hypre. So you can see that actually the one in Sparse or CUSP does not perform very well compared to the parallel CPU version. Actually, it's only faster than sequential CPU code. Actually, it's slower than OpenMP threaded CPU SpGEMM. But our implementation stays the fastest among all of them. So this is running on one GPU. The problem is from 500,000 to 16 million. So this is the breakdown of so after we put this together, we have a complete AMG setup on GPU. So this is the time breakdown of the AMG setup. So you can see that, I don't know if you can see it clearly, there's a PMIS direct interpolation, and you can see that the matrix still remains the most expensive part of the setup, and this shows all the levels. You can see the repeated, right, for all the levels. So, also there are some work in progress of building better interpolation on GPUs. For example, the classical collapsing the stencil idea of requires communications. So, but it's doable. It also requires accumulating the sparse rows, but it should be simpler than matrix product because the pattern of P is known, and we are also actually the best, one of the best interpolation in Hypre is the extended one. Is more complicated, but we decided to use a different approach to rewrite this computation as a matrix form. So in this way, we can reuse our developed matrix kernel to do that. And it turns out you can write it in a very nice form, just pre-compute some diagonal matrix and let the matrix kernel to handle the other difficulties. Okay, so in the solve phase, we have been studying some kernels like MATVAC, triangular solve. So we have a poster and there's a talk earlier this morning given on this in this conference about our effort on optimizing these kernels. Okay, here I want to show some numerical results. This is just model problems, Laplacian. So just want to give you guys some feeling about the speed up and the performance comparison on this model problem on GPUs. So we test 3D Poisson problem, 7-point first, and this is like quite a large problem per GPU, 300 qubit degree freedoms per node. And we use AMG with PCG, and so running on Laplacian, V100 GPUs and Power 9 CPU. So in the blue bar, if you can see it clearly, it's the direct interpolation of GPU, and the red bar is actually the apple-to-apple comparison. It's the same algorithm on CPU, so it's more like a 3 or 4 times speed up. Okay, so the first plot is the setup, the second one is solve, and the last one is the total time. So the extended interpolation is more expensive on CPU, but the solve phase is better because it's converged better. It's a better interpolation. So we hope after we implement the extended interpolation on GPU, we can still have a nice speed up on the setup phase, and we can also enjoy the fast convergence in the solve phase. So, and next is similar result, but for 27-point Laplacian, because the stencil is more complex, we have more work to do, so have bigger speed up. So again, if compare the same algorithm on GPU and the CPU, now we may have a 5 or 6 times speed up comparing CPU and the GPU. Okay. To conclude, the structured the structured and unstructured multigrid solver Hypre have been ported to GPU using different approaches. We use one thing I didn't talk about is we have a abstract memory model to ensure Hypre as one package that can run on different architectures. So we have abstract memory model to mapping the conceptual memory location to actual physical location on different platforms. So now, since the last release, we have one path of Boomerang MG completely running on GPU now. We are going to adding more and more support or options to Boomerang MG. There are in progress and future work we want to do. Since, as I said, the RAP is still the most expensive part on GPU, we want to take a deeper look at it. Maybe across the levels, there may be some clever ways to choose the algorithm to make the RAP on lower levels can be faster, because on lower levels, the matrix are smaller, so we can use more memory probably. And also, we are looking at the triple matrix product kernel on GPU instead of computing RAP in pairs. And we are implementing better interpolations on GPU. I have talked about some of them. We also want to think about other coarsening options besides the PMIS. And Steve and Kasha, we are looking at the more GPU appropriate smoothers now. And there's ongoing work is the Hypre IJ interface, how to assemble a sparse matrix on GPU directly. And more about software development of Hypre is using better memory pooling. We find that memory pooling is essential for the performance of AMG setup. And we want to have CPU-GPU runtime switch. So in future, you can say, I want to build an AMG and I want to I can run it on GPU or CPU at runtime. Currently, it's decided in the compile time. Okay, so that's pretty much I want to say, and thank you for your patience.